All right, this week we're going to talk about virtualization because it's super, super important and not many people talk about it, and it's kind of, there's a lot of like really scary, dense materials that are just super annoying to work through, and so it'll be great to go over it at a high level. So, oh and yes, it's of course the most important and best way to cloud your cyber. So the structure of this talk is we're going to talk about types of virtualization. There are a lot of different kinds, and they're kind of, it depends on how like broad of a scope you want to look at, what kind of falls under the umbrella of virtualization. So we're going to go over a bunch of different kinds and say how they're different and kind of the advantages and disadvantages as well as some use cases. And then because we are white hat, we're going to talk about some security, the general security model of why you'd want to implement virtualization and how that's been broken. So, right off the bat, there's some low-level stuff here I'm going to throw around and hopefully define a bunch of words. And I'm the first person to admit that I don't understand all of these technologies to the depth that they go. They're all, many of the projects I'm going to talk about are thousands and thousands of lines of C code, and they're really, really complex and have all sorts of different subtleties. So yeah. All right. So what is, what do we mean when we say virtualization? So I like to start with a really broad definition, which is going to be essentially any layer of abstraction. Okay, the talk is just going to get better from here. Any layer of abstraction implemented in a system which allows it to expose resources to a subsystem. And so that'll make more sense with examples. So what is it really? We've got a bunch of different types. So when we're looking at like a system, we consider hardware and software. We consider a composition of lots of small subsystems. And so we can talk about hardware emulation, where a virtual interface might essentially pretend to be the underlying hardware. And we'll talk about partial and complete emulation of various portions of the hardware. And then there's some, if you implement an abstraction of software all running underneath the operating system, then we can talk about operating system level virtualization, where under one operating system, you might kind of divvy up the resources of that operating system and expose different portions of it to, say, processes. And so that's kind of a very specific case, and we'll go over that. And then there are tons, just because systems are so complex, all of the little parts are equally complex, or at least add up to that complexity. And so there's tons of ways to do this, and there's tons of homebrewed solutions to doing this. We're going to go over major types and kind of very, very common use cases, so we won't really cover some of these more esoteric ones. So let's talk about partial hardware virtualization. So the range of different things we'll see kind of shows how broad of a term virtualization can be. So we're going to talk about the RAM chips in all of your laptops. You can look at that thing and consider it having a range of 0 to say 8 gigs or whatever. And at some point something has to refer to that full range in order to utilize the whole range. But every piece of software we write, we don't want to have to deal with that, essentially, because we're going to be stepping on this. How are we going to know if another process was using that segment of memory? If we just kind of look at it, it could be random garbage data. It could be, could have been something that a process was using before and then it went away, but it forgot to clean up. There's all sorts of stuff. And so if we just kind of abstract all the details out, then this will become a lot simpler on the software side. So yeah, this is what that is. This is virtual memory addressing, and you can see the word virtual cropping up. So we might have 3 processing running on a machine and say 4 or 8 gigs of RAM, and we actually might segment out that memory in order to allocate it more efficiently. Let's say process 1 goes, hey, I want a gig of RAM. And then, we make that happen. And then process 2 goes, I also want a gig of RAM. And so we make that happen. Then process 1 says, hey, I actually want half a gig more. we're not going to like push process over just because that's going to be really expensive. Instead, we're going to allocate over here, and then abstract the kind of division so that all process one sees is its contiguous block of memory. But what's actually happening in the in kind of the underlying hardware is this sort of segmentation. Some of you in your systems classes may have run into a segmentation fault when you break these rules. So now let's talk about full hardware emulation or virtualization. So we've talked about emulating part of the hardware. Now what if we talked about emulating the hardware for the whole system? So there's a lot of ways to do this, and processors offer basically interfaces in order to trigger this. We're going to go over the example of Intel VTX, which is a technology shipping on basically every Intel processor nowadays that allows you to do this. But essentially what full hardware virtualization lets you do is have, rather than a one-to-one of like, here's the hardware and here's the software running on top of it, we can switch between multiple execution contexts, and by doing that, run multiple systems on one set of hardware. So we might switch between one virtual machine and another very quickly, much like process context switching does, if you're familiar with that under a kernel, where we can switch between these contexts and offer each one some subset of the hardware's capabilities. Because this is so it's kind of complex to emulate the entire execution context. Oh yeah, go ahead.
So with full hardware virtualization, what's the difference? So I'm just sort of trying to understand this. Full hardware virtualization can just be seen as applying the partial virtualization to every aspect of the machine?
Theoretically, yes, but in implementation, no. For example, like Intel VTX is a way to essentially bundle up the whole interface to the hardware and just expose that to a virtual machine. Whereas, say, virtual memory addressing, the software is still running on the hardware in a single non-virtual execution context. But then when it uses the resource of RAM, for example, that interface is virtualized. And so again, in theory, yes, a full virtual machine is just all of the hardware being abstracted, but they're implemented very differently. Just because it would be very complex to emulate every single piece of hardware. It's easier to just abstract the whole processor and then offer that to virtual machines. Or VMs, if I use that, that's why. Okay, so Intel VTX. Essentially, on the Intel chip, you can trigger certain basic behaviors built into the chip, which allow it to kind of run multiple full execution contexts, where each one can be basically its own operating system. What this lets us do is
So like by execution context, I mean like basically two different things we're using the processor completely oblivious to each other. They
Exactly.
They have their own processor to themselves.
Yes, and rather than and I know that sounds, to a lot of you who've taken system stuff, that sounds very similar to context switching between processes. But this is actually abstracting that whole thing. And actually within the operating system that's being virtualized, it's also doing, it's regular process context switching. And so it's, you can end up with situations with lots of nested virtualization.
So it's like the same thing but another layer.
Kind of, yeah. And again, it's implemented very differently, exactly. So yeah, VTX lets us do this on Intel chips. There's an AMD equivalent, call it AMD-V. And this is great. This lets us run, say, multiple systems on one processor at the same time. But it's also complicated because let's say my hardware has like a floppy disk drive. Well, I have to be able to abstract that interface if I want to share it between multiple VMs. And no one uses floppy drives anymore, which means no one is really looking at that code. And so about a year and a half ago, there was a buffer overflow vulnerability in the floppy disk driver in the virtual machine abstractions that a lot of people were using. And it's no good when a VM can gain code execution in the context of what's running the VM, which we'll talk about later. But yeah. Okay. So the hypervisor model. So we can have all of these systems running, but like what actually runs them? And the answer to that question is a hypervisor. There's two types, which I'll go over, type 2 and type 1. A type 2 hypervisor is something like an application, which is running under an operating system, for example. I don't know, some of you may have run VirtualBox or VMware. All of these are hypervisors in that they allow you to manage and implement the abstraction between the VMs and the host system. A type 1 hypervisor, on the other hand, is something that you're running on the bare metal. In the diagram here, it says host OS or Bootstrap. The host OS is something that runs the application like VirtualBox, which then runs all of the virtual machines. What it means by a Bootstrap is something that essentially starts the hypervisor. So when you're running a type 1 hypervisor, it's not really at the same layer, if you will, as an application like VirtualBox. It's a layer below, if you will. Do you have a question? Okay. And then, of course, that if the hypervisor is running directly on the hardware, then that's that layer. Otherwise, we have that one further layer of abstraction. Yeah, so that's what a hypervisor is, something that's running, kind of starting all of that up and managing all of your different virtual machines and making loud motorcycle noises. Okay, cool. And so then a common use case for the hypervisor what is that? Okay, Google is not handling my images properly. That just says AMDV under the corner of AWS there. One example of a bare metal hypervisor, type 1, running directly on the hardware is Zen. This is an awesome project. You could say I'm personally invested in. I run an operating system based on it, which allows you to essentially manage all of your virtual machines in a very kind of efficient way. And the hypervisor, Zen specifically, is a very small code base compared to like a full Linux kernel, which of course gives it a smaller attack surface, increases or decreases the likelihood of vulnerable code, which is always good. And then two kind of instantiations of that. AWS, Amazon Web Services, basically the largest cloud platform in the world. You request a virtual machine from them, and they'll spin up the machine and give you access to it, and they can do that at colossal scale because they can virtualize tons and tons of machines on really nice hardware, or anything from cheap hardware to really nice hardware, and just expose to you what looks like a full machine but is in fact a virtual machine. Yeah, and so this has much less overhead, Zen specifically, than full hardware virtualization. And the way it achieves this is what's called para-virtualization, which is essentially like some developers going through and going, what's hard to do in a full virtual environment? Stuff like sharing memory to the GPU and like interfacing with device drivers. All that stuff is not great to do from a virtualized context because it needs to move memory in and out of that context, and that adds a ton of overhead. So let's take those things that are hard to do, and let's just do those in the underlying hypervisor, which is talking directly to those devices, and just essentially get rid of that overhead. So a VM might ask the hypervisor to send some memory to the GPU. It'll do it rather than having to itself trigger that event and go through multiple layers of abstraction. Because you want stuff like that to happen very quickly, and so para-virtualization lets you do that. But yeah, Zen's cool. And then, as with anything, Zen has had multiple privilege escalation vulns, but much fewer than anything else than tons of other implementations. Okay, so now let's talk about. I brought up operating system level virtualization. This is the abstraction of things that are already defined in the software. We're not abstracting processor resources and devices at this point. We're abstracting things like the file system, and then as well as we do, in fact, abstract stuff like the processor and resources, but we do that another layer deeper, if you will, underneath the same kernel. So you're running one instance of an operating system, which is then scheduling out its resources between these isolated virtual machines. There are multiple technologies which do this, everything from LXC, Linux containers, and C groups, which allows you to essentially assign resources to a process and manage how those are distributed. And then and the combination of being able to manage processes with being able to manage the namespace. So the stuff that one machine knows about is completely isolated from the stuff, if you will, that another machine knows about, the memory it can work with, the files on the system. And so putting those together, we can actually run operating systems underneath other operating systems all in one kernel. And a common implementation of that you may have heard of is called Docker. Docker initially has used Linux containers for in its implementation, as well as a couple other libraries which allow for management and process control, like libvirt and cgroups, respectively. And what this does is it lets us run like multiple versions of Linux operating systems under one Linux kernel. And because it's sharing the kernel, you don't get the option of running totally different OSs like you do with paravirtualization or hardware emulation. And so you can see this, because we're not scheduling between huge, colossal execution contexts. Instead, we're just scheduling between these resources. We have much, much less overhead. This is really nice, but it does lead to a weaker security model in that we are still sharing resources a much more, much closer to each virtual machine. And so if you look, you can see this the weaker security model kind of express itself in the fact that Docker has many, many more privilege escalation, sandbox escape type vulnerabilities than, say, Zen. But that said, it lets us do really cool stuff, so we use it anyway. So I've brought up execution context and sandboxes a couple times. So this is all kind of under the purview of the security introduced by virtualization. Every time we abstract something underlying, this allows us to essentially, it gives us a further layer wherein we can implement controls. If we're just saving things directly to, say, physical RAM, doing writes, and we give software the ability to write directly to physical RAM, say, then it's going to be able to overwrite physical RAM that we've assumed another process was using. By implementing an abstraction, we can control what's using what, gives us a stronger permissions model, which is critical to security. And the other nice thing is that in many implementations, it gives you a secure implementation by default, just because it by default separates everything. If you want to share memory or share a device between two virtual machines under Zen, you have to explicitly enable that, which is really important. So the security model is essentially in the isolation that we gain. Yeah. Oh, sorry. Was that a question? No. Okay. Cool. All right. So let's talk about what exploits have looked like. When you're running multiple systems underneath one underlying, say, hypervisor, you've got a couple threats. One is denial of service. If one virtual machine can trigger events which don't allow you to start any new virtual machines, or say block the processor on that virtual machine, or say, bring the whole system to a crawl, that is a breaking down of that isolation between two virtual machines, because one virtual machine suddenly can't do anything, and if it were a full system, it would be unaffected, which means that's a failure in the abstraction. So that is a threat, a denial of service. Another threat would be an information leak. If one virtual machine can read information that's supposed to be isolated to another, then, for example, if you rented an AWS instance, you could suddenly look at everyone else's AWS content, which would be terrible because people often do anything from password hashing to serving DRM using AWS. And then the final and kind of most severe threat to the security model would be a sandbox escape. If you can actually go from being able to execute code within a container to being able to execute code either within a different container or as the hypervisor, that's obviously a catastrophic failure. If you're running, an application and everything's supposed to be going nicely, and suddenly a different VM can just take control of that, that's the security model has failed. And so some recent exploits in this category have all been really, really cool. For denial of service, a little while ago in AWS, AWS does some nested virtualization, which is really fun. They have actually we can draw a diagram. we might have two virtual machines and abstractions to the processor running both of them. But then beyond that, we actually share a GPU abstraction between one bundle of VMs and another. And there's a bridge which allows these to communicate with the GPU. And so if we're doing, password hashing at scale, for example, then each VM we're using is going to be communicating with the GPU over this bridge. And this maybe you own this VM, and this VM belongs to Netflix, and this one belongs to someone else, et cetera, right? But they're all sharing the GPU on this bridge. There was a zero-day vulnerability in AWS which allowed you essentially to trigger behaviors in the GPU where you just essentially stress test the GPU, and it would happily just run whatever you told it to, which means that it would completely ignore requests from every other virtual machine. And so obviously there's a failure in the bridge, and which allowed for denial of service on the other VMs, which of course isn't the end of the world, but it's still a vulnerability. This was a really fun project to work on. I just started running an old piece of code called IV GPU tools, which are just made for stress testing your GPU. And I found that when I essentially asked the GPU to do its capacity of work, to test the limits of how much work it could do just by hashing lots and lots and lots and lots of stuff, that it would DOS the other VMs on the same bridge. And so I got to report this to AWS. Let's see, that was 4 years ago, which was a lot of fun. And it's since been patched, and disclosures have been responsible and such. So we're all good. But that was fun. Cool. Okay. So then information leak. There was a really cool vulnerability even more recently. Guess what? Also in AWS. AWS is such a widely used piece of infrastructure that vulnerabilities are found much more commonly. Okay, so this one's awesome because it actually refers to two things we've talked about: virtual memory addressing and paravirtualization. So let's say we have an abstraction of RAM for two virtual machines, and this RAM is made up of pages, which are little separations of little segments of it. And so what Zen would do is it would offer this abstraction of RAM. So if a VM requested some memory, it would give it to it. But it wanted to do this efficiently. So let's say VM1 and VM2 are running on the system. If VM1, say, loaded libc into memory, like the basic library that contains all of the standard C functions, if it loaded into memory, let's say it did that here. So now that exists here. Now VM2 does the same thing. All it would do is it would say, hey, that's here, because all of this is running on the same physical memory. And this was fine on its own. But then VM2 was like, you know what, I actually want to modify some of the content of this page. And so then Zen would be like, oh, well, I guess I have to copy all of this over, fill this in, and then make the changes. Let's say, those changes are in another, And so that would take a while. That would take a lot longer than if I, say, had something here and I just wanted to make a change and made the change immediately, because it's introducing this whole what's called copy on write. And so VM2 could go, well, I think this memory is here. And so I'm going to try to allocate the same thing and then change it. And if it takes no time at all, then that memory wasn't copy on written. If that took way longer than that, then it probably was copy on written. Some other VM in my cluster also has that exact same page of memory that I just copied. And so you're probably not going to guess a password's location in memory and then be told whether or not that block is in memory, just because that's a very small offset. You'd have to find the exact points. But with something like libc, that's going to be allocated often at a fixed offset in some programs, and so you can much more easily just kind of page through memory and go, oh look, I found it because I hit the right offset, the correct page, and it got copy on written, and it looks the same in memory, which makes it much easier to find, and it runs on basically every Linux. Every Linux VM is going to have it loaded into memory somewhere, almost certainly. And what this was an information leak on its own. It also allowed for what's called an ASLR bypass, if you want to Google that at home, which was also cool. You can chain it with other vulnerabilities to learn more about what your target VM, say VM1, looks like, and in order to take control of, say, VM1. But this was, as you can see, horizontal information leak in Zen. And then finally, sandbox escapes. There's been all sorts of work to kind of fuzz, which means just throw input at the abstraction that, say, the hypervisors run, because there must be a way to request memory. There must be a way to talk to a device indirectly, and so that interface is not going to be perfect. And so people have basically just run whatever they can against that interface just to see the behavior. And there have been a few things that have led to exploitable crashes or just unintended behavior in the interface. And so people have been able to find vulnerabilities which allowed them to, say, escape the kind of boxes that the hypervisor put them in. And those types of vulnerabilities are usually really, really kind of weird and gross, because it was like, I threw a 7 at the GPU interface, and then it exploded. And so someone will implement that in C and be like, look at my awesome vulnerability. And you'll look at it, and you'll see, like, at the top, like, hash define magic number 7. And it's like, why? Why? You don't know until afterward why it makes sense. And so they can often be kind of hard to look at in retrospect from an outside perspective. But they do exist and have been found often by fuzzing these interfaces. Okay. So yeah, I want to open this up to question time. But thank you for listening to my overview. And yeah, so are there any questions about any portion of this, or questions about none of this at all? Just whatever. I want to open it up. Luis.
Could you tell us how you use cubes?
Sure. Okay.
Oh, no.
So by popular request, I left it out of this presentation, but you've opened the gates. So Cubes, as I said, implements the Zen hypervisor, but it does it on a desktop, which is currently being used to present this lovely slideshow. And what that lets me do is that lets me run virtual machines. I'm currently running 5 or 6 Fedoras, some Debians, and I'm working on getting OpenBSD running because they also just implemented paravirtual interface. But yeah, Cubes is just a lot of fun. Running those VMs leads to really nice security implications. If someone figured out a way to go from docs2google.com's JavaScript to remote code execution on my machine, then it would be limited to this virtual machine. They wouldn't suddenly be able to view my passwords in a password manager, because that's in a completely different virtual machine. So it lends itself to a lot of security. It's really lightweight because it's using paravirtualization, and yeah, it's cool. Was there anything specific, or did you want to? All right, more questions. Yeah, Nick.
So does AWS still do copy on write?
No. So after this was discovered, they would have if it had just been an information leak, because they decided it was too hard to guess where things were in memory. And then someone showed them, yeah, but if I can guess where an important function call is in memory, and then I also have, say, a buffer overflow vulnerability, then I can overflow the buffer in a program, jump to where I know that important function is, and make and get that function called. And so, because of the impact that came from chaining it with other potential vulnerabilities, they decided, yeah, we need to fix this. And so they upstreamed a patch into Zen, which basically stopped it from doing this, which is called deduplication. They just disabled deduplication across the board. So we lose a little bit of performance, gain a little bit of security. Nick.
I was going to comment on the copy on write thing, but you basically said it. Yeah, no, that whole behavior comes basically because it comes from the Linux kernel, and so they were like, oh yeah, this is a cool thing that's there. And then, yeah. So the performance loss is not actually that big because.
Or even not about. Oh, sorry, Jasper.
How's the coffee?
Coffee's delicious. Questions about? Yeah, go.
We're kind of learning more about this stuff because I've actually never heard of virtualization before. So
Definitely.
kind of getting exposed to something like this is really like fascinating in a way.
Mm-hmm. And so, yeah, like I said, a lot of this stuff is like by necessity implemented at a very low level. And so sometimes when you approach it, you just kind of have to grind through just like being like, okay, this is complicated, this is some magic, but I get what the whole thing is doing. And don't get too bogged down in the details. But if you look at projects like, I really like whenever like vulnerabilities in Zen come out. Like I wouldn't want to look at like the whole Zen like code base just because it's going to be doing all sorts of different things. But like if you look at like write-ups about vulnerabilities in Zen or write-ups about sandbox escapes from say Docker, then you can learn about like, oh, that broke because this was implemented this way, and you learn like a little bit about it. And then just doing that repeatedly and just going through like the annals of vulnerabilities, you go like, oh, okay, I get why that broke. It's because this was implemented this way, and then they patched it. And so I feel like that's a really nice way to approach it is through like how it's been broken. Again, like I said, some of those can be really weird and just like, how did they come up with this? Most of it's fuzzing, just throwing garbage data at it until something exploded. But yeah, so don't get too bogged down in the details and just lots of Wikipedia, lots of write-ups. Definitely, definitely. The syscall interface is, in a way, an abstraction. It allows processes to run things in the kernel that need to be run in the kernel for speed and security and privilege separation. Yeah, other stuff. Please.
Is there a difference between virtualization and emulation?
So I kind of threw around abstraction, emulation, and virtualization almost equivalently. Emulation just means it's implementing the same interface that something else does, whereas abstraction just means it's putting a layer of code between something and something else. And so an abstraction can be an emulation, and virtualization can be the implementation of either of those. And so I use them basically equivalently. But so semantically no, but in this yes. Nick?
What happens if I try to run a hypervisor inside a VM?
You'll probably see a severe performance lag.
Sadness is the answer, because at that point you've got like virtualizations inside your virtualizations, inside your partial virtualizations, inside your complete virtualizations, inside your file systems, inside your shroots, inside it's just all there's running like saying, hey, put this in RAM suddenly becomes like, hey, this guy told me to put it in RAM. I should go tell my boss. Okay, let me run over to the Department of RAM and tell them to store it. Okay, here you go. Oh, okay, let's make an archive request and put this into RAM somewhere. It becomes, almost bureaucratic in the way that it works. And again, some things require being able to talk directly to the hardware. Everything from like model-specific registers, which are spots, little. If you're familiar with registers, they're kind of like scratch workspace in a processor that can be accessed very, very quickly, much more quickly than RAM. And so some manufacturers will take an Intel chip and then add some registers, or a manufacturer will take another manufacturer's chip and just change stuff. And some of that stuff is just not even documented. And so if you're running something that's meant to be run on that chip, then suddenly that needs to be abstracted. Maybe it wasn't implemented in the abstracted interface because it expected it to just work. Then it's just going to explode. A great example is running cubes on a MacBook, because there's model-specific registers in there that are meant to tell the hypervisor how many CPU cores there are. And an abstraction of that, it doesn't, Zen doesn't know to report, doesn't know to check MSR 35, model specific register 35 for that number. And so when a VM goes, hey, I'm looking for the number of CPUs you have, it just goes 0. And then the virtual machine is very confused. So it's like, what am I running on? And then it explodes and dies. It actually segfaults the kernel of the VM, which is awesome. So yeah, it's no good.
Actually running on a GPU, that's why report 0.
Running on a toaster.
Hey, NetBSD well.
Nick. So this might be more of an implementation question, but does the fact that you're exposing a new higher level, you're basically exposing a new higher level interface with the introduction of virtualization.
Mm-hmm.
And so does applying virtualization add a lower bar to how, like, for example, what programs I can run? Like, for example, can I still run my bare metal assembly programs? If I want to run my assembly on Zen, is there the Zen ISA? Is it follow the Intel ISA? How would I go about that?
And so yeah, that is the actually kind of idea behind perfect abstraction. Perfect abstraction, you can do exactly what you were doing before. It's just being handled and then handing that down. So if you say have like a specific instruction that's supposed to do something, then you run that directly on your processor and it does the thing. In a perfect abstraction, Zen would say, oh, he wants to do this thing, and then do that thing on the hardware and then report that it had been done. So in a sense, yes, it's still running through the abstraction, but it's doing the exact same things. Unfortunately, not all abstractions are perfect, and they might change what you were doing, being like, no, you meant to do this. This is better, or this is faster. And so, you might run into problems if you wanted a specific set of instructions run, for example, or like a specific way of talking to a specific device. The abstraction may not be perfect, and you may lose some of that specificity in the kind of exchange. But in theory, yes. Anything else? We've had a lot of super low-level specific questions. Feel free to add just like any level of question you want. Why? I can't think of questions. That's why I didn't put them in my talk. Yes, Nick.
So if I want to, I'm not ready to commit to cubes. I'm not ready to commit to my type 1 hypervisor. But if I would just want to run some virtual machines, what do you recommend for a type 2 hypervisor? What do you recommend for a program that does virtual machines?
Sure. So it's fun to experiment both with operating system level virtualization and stuff like what VirtualBox and VMware do. So Docker has a nice command line interface, which is kind of cool. Being able to run OS level virtual machines. You play with that, see how it's kind of a little bit faster, but a little bit more limited in that you have to share the kernel. And then when you want to play with hardware emulated virtual machines, hardware virtual machines. So your choices aren't great. The two most common ones are VMware and VirtualBox. VMware has a free version that's a little bloaty, but works pretty well. And there's VirtualBox, which was implemented up to a point pretty darn well, and then taken over by Oracle, and since no changes have been made. So literally we're like, we're going to eat this and then not do anything. And so Oracle is just kind of holding on to it, and so it hasn't been updated since, which is very sad.
Hey, just like Java.
Yeah. And will theoretically then reach its demise some point in the future. But it does work well, and it's a little more lightweight than VMware. Both of them do really cool things about snapshotting, which let you say roll back to a specific state the VM was in. Both of them do support a wide range of operating systems, and both of them run relatively quickly. I think there are tons and tons of benchmarks online as to which one works better and faster, but If you're just messing around with it, then you can experiment with either. Nick.
What's the JVM?
The JVM,
Oh,
the Java
Jesus.
so that is effectively a partial abstraction of instructions on the processor and instructions that spit out of the Java compiler. So if you take a language like C and then you compile the code, it goes through a couple of intermediary stages, but what comes out the other end is something that the processor can execute directly. Machine instructions, yeah. And whereas what Java likes to do is it likes to run the JVM, which is its own process, which is running on. Let's ignore other virtualizations. So we'll say the JVM is running on in the processor, and then it receives the compiled Java code and figures out what that kind of mapping needs to be from what the compiled Java code wants to do to what needs to be done on the processor. So it is essentially a layer of abstraction between the processor and the code.
So the JVM isn't a virtual machine?
So it is with a very specific use of the word virtual, because there's like we saw here, there's like tons of different things you can refer to as virtualization just because they implement abstractions of underlying systems. And so it is to an extent, but it's not a virtual machine in the way that like a Docker VM is a virtual machine. They're all doing different things.
So a lot of the times when you hear about browsers, you hear about browsers as sandboxes. Does that mean browsers are also virtual machines, kind of?
So to an extent, again, you can use these words super like kind of flexibly, which honestly I think makes it harder to go and learn about, just because you might run into 8 different instances of the word virtual, and it's like, how do these connect? So if we take like a JavaScript engine, for example, it might be doing exactly or similarly to what the JVM is doing, where it's taking in that the JavaScript code and figuring out what bytecode needs to be executed in the processor. And so there's a VM in that sense. In the sandboxing sense, the operating system might and the browser might interact to say that the browser can only ever write to like downloads and folders in downloads, for example. That is in a sense a sandbox, because it's emulating the file system by saying, here's some portion of the file system. That is your file system. And it's doing that in tons of different ways. Like maybe it only has write access to downloads, and maybe it can only read from specific places. And so it's putting a layer between the browser and, say, the file system, or between the JavaScript that's executing and or say the JavaScript that's executing from one page and the JavaScript that's executing on another page. It's enforcing these boundaries by, rather than just running the code directly, putting a layer of abstraction in, figuring out what goes where, and then dealing with it on the hardware, for example. And so yes, there's multiple ways to refer to that, but yes, essentially. Anything else? Nathan.
Where can I learn more about cubes?
So the Invisible Things Lab are the creators of cubes. There are a couple crazy Ukrainians out in fending off the Russian government, and there's some awesome hackers out there, and they have a blog. The Invisible Things Lab blog talks about everything from why Intel x86 should be considered harmful to the newest features of cubes to all sorts of cool stuff. They have lots of awesome write-ups. Their code is really good. But yeah, so the cubes has tons of documentation, and some of the management scripts are written in Python, which is really cool because you can just pick them apart and it's super readable. And so yeah, the site, the docs, and using it. Anything else? Yeah.
So this correlated then to like cloud-based platforms and how security is implemented with that in your virtualization?
Yeah, so for example, using the example of like AWS again, because you're running your stuff in one virtual machine and someone else's stuff in another virtual machine on the same hardware, that layer of abstraction lets means that one VM is not going to step on the other's toes, even though they're on the same hardware. And so, yes, that contributes to the security model, as well as just being able to run multiple systems on one piece of hardware, which just makes everything more efficient. Suddenly, we don't have to commit hardware to one machine. We can say, oh, well, they're not asking for much computation right now, but they're asking for a ton, so we'll allocate. Or they're both asking for tons of processor resources, so we're going to schedule it out 50-50, for example. So it's
this stuff is being run on servers then, I'm assuming.
Yeah, exactly. At some point, it does have to be running on hardware, no matter how many abstractions are between, say, your process and the hardware. Yeah.
Have we found anything like cubes for mobile devices?
Yeah, mobile devices are weird. A lot of them run on the ARM architecture, and so I haven't personally looked into that much. I highly doubt Zen as is would run on. Oh, you know what? They actually are working on an ARM architecture implementation of the Zen Hypervisor. I just remember that because I was reading about that in their blog. So it's being worked on. Again, when you're scheduling out resources to tons of VMs, it's much easier if you have lots of resources to work with. Like I have 16 gigs of RAM on that machine, which means I can run about a dozen VMs comfortably. But if you're scheduling out the gig or two that's on a phone, you're going to have to run some really, really lightweight VMs if you're going to want to do it. But it's being worked on.
There's a white paper on it. It's really cool.
Oh, cool. Apparently there's a white paper out on it. I don't know what stage of development they're in. They're probably running into some really interesting problems with the fact that the ARM architecture happily changes year to year.
And the fact that most phones don't have an L3.
Yeah, again, that's the processor actually will implement that abstraction for you, but yeah, there's lots of issues.
The perspective of not like eating it too horribly.
Oh yeah. Again, when you are running a bundle of virtual machines, you've got to think about resources. You can if you allocate a dozen machines on 1 gig of RAM, there's nowhere they can go aside from stepping on each other's toes, and a good hypervisor won't let them, but it'll also then not have any resources to give them. Yeah.
So, do things like VirtualBox and VMware have any features that cubes don't?
Yeah. Well, one is that they can be run under multiple operating systems. You can't really run, like if you ran cubes underneath an operating system, like in VirtualBox, for example, it'd be super slow, and I think it would. I don't think it works very well. I think it works, but it's so slow that it's just kind of unusable. And so, yeah, VirtualBox does let you say, run a bunch of things underneath one operating system. That said, there's a lot more work going into Zen and cubes, for example, than there is going into VirtualBox. And VMware, their free version, they just kind of were like, here, we're going to make this free, but then make all the cool stuff paid. And so you can get some really cool features in the paid versions of VMware, but again, it's expensive. Yeah.
Just, if anyone is interested in virtualization, Cal Poly gets VMware Pro for free.
Oh, really?
Yep.
Cool. Yeah, in that case.
Yeah, it's part of Spark.
I would choose, yeah, go ahead. I would choose VMware Pro over VirtualBox any day of the week.
No, not at all.
Yes, that's one other thing that's kind of annoying. But yeah, if you need to leave, feel free. And aside from that, any other questions? I think we can call it good then. Thanks, everyone.